Welcome to the lecture of Mathematical Fundamentals in Pharmacokinetics, Part 1. You can find more detailed information about this lecture from the textbook, Chapter 2. This lecture has 4 learning objectives. First, to identify the order of reaction of different processes and explain how the order can define the equation that determine the rate of the reaction. 2. Represent the pK data graphically using Cartesian coordinates or rectangular coordinate system and semilog graphs. 3. To define rate constant, and order process of drug elimination, and then calculate the pK parameters from zero and first order kinetics from experimental data based on these order processes. And last, calculate the initial concentration at the time, K, half-life, volume distribution Vd, and AUC, and then express the calculated and theoretical pK values in proper units. The important basic pK parameters are elimination rate constant, K, or in zero order you call K0, half-life, volume distribution Vd, the initial amount concentration of drug CP0 or concentration of drug at any time t, AUC, clearance. In pKs, there are two terminology you need to distinguish, that is the rate and the elimination rate constant. Rate is the speed at which the amount or concentration of drug changes during the absorption or elimination. Elimination rate constant is a value used in the pK to describe the rate at which a drug is removed from the system. It is often abbreviated as K or Ke or Kel, and for the zero order kinetics you have K0. The name tells you the value. Elimination rate constant, the K value is constant for a drug. There are two important orders in pK is zero order and first order. Zero order is also called nonlinear process. In this process, a constant amount of drug is eliminated per unit time. For example, 5 mg of a drug is eliminated per hours. This is zero order kinetics. This rate of elimination is constant under the total concentration of drug in plasma changing. Zero order kinetics is rare, it's not common in pK. Mostly it happens when the drug is under controlled release or the drug is given by IV infusion. The most common order process is first order process or first order kinetics. This is considered linear process because the rate of elimination is proportional to the drug concentration. So that's we call linear process. And the linear and in this one, the fraction of drug is eliminated per time based on the first order kinetics. Half-life is one of the most important pK parameters because it relates to the calculation of the frequency of dose. For example, if you see the drug has it should be used 2 times a day. Some drugs use 3 times a day, 4 times a day, or once a day. Why and how can you obtain that value? The calculation of frequency of use is mainly based on the half-life of a drug. Half-life is the amount of time required for the amount or concentration of drug in the plasma is reduced by a half. It is abbreviated as a T-half. For every half-life, a half of drug remaining or a half drug will be reduced. For one half-life, 50% of drug remaining is compared to the initial one. 50% of drug remaining and 50% of drug is eliminated. For 2 half-lives, after another additional half-life, 50% of 50% here is decreased. So that means 25% of drug now remaining in the blood. And additional 25% elimination here plus 50% of both, you have 75% of drug eliminated. After 3 half-lives, a half here reduced. That means 12.5% of drug remaining. And for the elimination, 75% here plus a half at here. So you have 87.5% of drug eliminated and so on. In general, a drug is considered to be removed almost all out of the body when 94 to 97% of drug disappear from the blood. And it takes 4 to 5 half-lives. In PK calculation, usually they assume after 4 half-lives, most of the drug will be eliminated out of the body. Two other important PK parameters is the concentration of drug in the plasma. There are two types of concentration. First one is initial plasma concentration. That means the maximum concentration or the initial concentration appear in the blood at the highest for the IV bonus for IV injection. And the abbreviation is CB0 or C0. This one is important. The C0 is very important to build the equation of the formula to describe the plasma concentration of drug at any time. Remember that in practice, you just can't withdraw the blood at some time point from the patient. You cannot take the blood all the time, just some time point. And from the time points, you have the time, you have the drug quantification in that volume, so you can calculate every time point. You have the time associated with the drug of concentration in the plasma. And from certain time point there, you build equation, and then you can predict the concentration of drug at certain time that is not in the same time that you withdraw the blood. So that's the meaning of the calculation of the concentration of drug in the plasma at certain time. And that's it called CBT or CT. The other important parameter is the volume distribution and clearance. Volume distribution or apparent volume distribution or hypothetical volume distribution. This is the volume in which the drug is assumed to be uniformly distributed in. Clearance defines volume plasma clear of drug over a specified time period. Volume of distribution clearance are all important because that relates to the adjustment of dosage regimen for the patient based on like how much was the dose that drug need to be given to the patient at the beginning, loading dose, and was a maintenance dose or was a dose like continuous to give to the patient. This is a little review on the slope. There's 3 kinds of slope. When the slope is positive, what happened between in the x bar, that's increasing of any value, increasing value of x, you have increasing values of y. That's when the slope is negative. That means it's larger than 0. When the slope has no change, with each value of x, the value of y is constant. There's no change. Then the slope is 0. And for the case when with any value of x, there's a decreasing value of y. Increasing value of x, you have decreasing value of y. So in this case, the slope is less than 0 or we call negative. How to calculate a slope value? For this scenario, a y value, the values of y decreasing with an increasing of x. The slope is calculated based on the equation here. For every value, for each time point, for example, you have 2 time points. x1 coordinate with value of y1. x2 coordinate with value of y2. For each time point here, you have a pair value of x and y. x1, y1, x2, and y2. The slope is calculated by y2 from here minus y1 divided by x2 value here minus x1. So this is the equation to calculate the value of slope. And the slope, in this case, the slope value is negative. For the equation, this is slope. For the equation to describe the line, the straight line here, is the y equal to b plus mx. And m here is the value of slope. You can calculate or you can find out from the graph or from the value in here. X is any changing of x, then you have different value of y. And b is the intercept. B intercept here in case the line here cut the y here. The value dash x is 0 and y and cut the line cut the y bar here is a b. So for any data with the scenario increasing of x associated with decreasing of y like this, you can calculate the slope based on the time point pair here like this. And then the straight line can be described by the equation y equal to b plus mx. M is the value of slope, b is the intercept, or the value when the x equal to 0 or when the line cut the y bar. Now we review about the presentation of rectangular versus semilog on the graph. For this graph here, you can see for any changing in the unit of the x bar or y bar, any changing is proportional. For example, from 0 to 1 equal to 1 to 2, equal to 2 to 3, etc. And from the y bar 0 to 1 equal to 1 to 2, equal to 2 to 3. So the unit here on both bars, x bar or y bars, are proportional. So for this case, the paper we call rectangular paper. And any decreasing of value of y bar associated with increasing value of x, the straight line like this, is described by the equation y equal to b plus mx. And again, m is the slope, b is the intercept when the line cut y at when the x value is 0. And the slope is calculated is here. What is semi-log graph? In the semi-log graph, it's a little bit different in the y bar. For the x bar, there's still a proportional division between time point. For example, 0 to 1, this means 1 unit is the same distance to 1 to 2, the same 2 to 3, etc. This x bar. However, in the y bar, it's not like the proportional distance anymore. There's something changed. The value from y bar is taken logarithm here. So the y bar becomes the log bar. It's not like regular bar anymore. And you can see from the log scale, it starts with 1, not start with 0. 1, 10, 100, and if it's increasing more, it can be 1, 10, 100, and then 1,000, etc. And after 1, it can be 0.1, 0.1, and the value of the y bar is always more than 1. So again, look at this graph here. In the graph, in the log scale of the y, we see from 1, and this is 10, this is 100. So where is it 2? 2 is here, 3 is here, 4 and 5, and so on under 10 here. You see the distance here is not proportional because the value here is a logarithm. It's not like value of 1, 2, 3. It's the value here is a logarithm. That's why when you can see the stick divided here is different because it's follow the log scale. We call semi-log graph because just only y bar is take the value from y bar is take logarithm. The x bar is still normal value, so that's why we call semi-log paper or semi-log graph. Any straight line represent the decreasing value of y bar associated with increasing value of x bar is described by the equation y equal to b times e exponential mx. Let me explain a little bit about this one. Because this the straight line here, it follows a little bit special when the y bar values is in the logarithm scale. The slope for the line here is calculated based on the natural log. For any value time point of, for example, x1, x1, y1, x2, y2 here, the slope is calculated by natural log of y2, value of y2, subtract natural log y1, and then divided by x2 minus x1. And because that's the decreasing here, the slope always has a negative value. And the equation to describe the straight line is y equal to b e exponential mx. B is the intercept when the line cut the y here. M is the slope. So if you know the value of the slope, the intercept, for any changing in x value, you will have associated value of y bar here. Understanding about rectangular versus semi-log and the graph in different kinds of scale here is very important for you because it's very similar to the way of the pharmacokinetics behavior in the zero order and first order. Now we go back to the plasma concentration versus time curve in the pharmacokinetic. This is for oral administration, one compartment. And the line here represent like when the drug taken orally, it takes time for the drug to be absorbed to the blood. And when it reaches the maximum here is the concentration of drug in the blood will be reduced because of the elimination, and until all the drug is eliminated with time. So we know that at the peak line here, the peak concentration, there's an equilibrium state between the absorption and elimination. After this equilibrium state here, the drug concentration will be declined. And this phase, the decline phase here, is called the elimination phase. And to calculate how much or how fast the drug can be eliminated out of the body, we use based on this phase to calculate. For any drug that's taking IV bolus injection, the drug will go directly to the blood. And in that case, the curve will be represented like this. For IV bolus, from the beginning, because the drug, 100% of drug will be in the blood, so you have the highest concentration here. And in the blood, when all the drugs are on the blood, there will be very quickly, there's an equilibrium state between the drug in the blood and elimination, and the drug will be reduced with time immediately after that, and it will decrease with time. And in case here, the line here, it shows kinds of first order kinetics. For any drug follow two compartment model, the drug will be reduced, but there's a two phase, distribution phase and elimination phase. When the drug in the concentration of the drug in the blood reduce, because at that time it go to the blood and then it go to the tissue. So that distribution phase, we see it reduce, but actually that's not elimination phase yet. After the distribution phase is established with equilibrium state, then the drug will be eliminated. And for the two compartment model, the elimination phase is obtained at this straight line here after distribution phase. In pharmacokinetic calculation, zero order and first order are the most commonly used of order to describe the elimination of a drug. Look at the graph on your left. That's about zero order. And the graph on the right is about first order. Now we go to zero order. Look at this graph here. When the blood is collected from patient over time. For each the time point, the drug concentration is quantified. And from the data of drug concentration from many time points, a graph is constructed and plotted. X bar to represent the time to collect the blood, and the Y bar represent the drug concentration or drug amount appear in the blood. Please note that when the blood is collected, plasma or serum is used to quantify the drug in there, because the whole blood is very difficult to use to quantify the drug when there are many other components can interfere with the assay. So when we say, that's why we say plasma drug concentration or plasma drug amount. Please note that plasma or serum is used instead of whole blood. Alright, so after many data from each time point, for each time point, there's a time against the concentration of the drug. Each time is associated with the point here is associated with the time and the drug concentration. So when you link on the point together, and when you plot first in the rectangular coordinate, and the line is a straight line like this, the drugs is considered follow zero order elimination. And then in the zero order elimination with the straight line like this on the rectangular coordinates, the slope is used to calculate the rate constant of drug in the zero order to represent the decreasing the amount or the concentration of drug decrease over time. And the equation to represent the line here is used to represent the decreasing of drug over time. So as we know that any straight line like this in rectangular coordinate, the slope is calculated with this equation, and the line is represented with this equation. We adapt it to the pharmacokinetic use. The slope for this line always a kind of negative value, and the rate constant K to represent the amount or concentration of drug decrease over time. It has a negative value. So rate constant K is calculated based on the negative of the slope. For any 2 points, if you know the data of the time and the drug concentration for any 2 points, you can calculate the slope and take the negative of slope, you have the rate constant K. That's for zero order. And as you know that when the blood is withdrawn from the patient, you can construct a straight line like this, or the plasma concentration or plasma amount versus time curve. You cannot wait to take the blood until no drug is appear in the blood, because it's not feasible. And practically, just some time point is collected, or it's just some time point that the blood is withdrawn from the patient. You cannot withdraw the blood like every day or for a long time. You need to predict when the drug is eliminated out of the body at a certain time based on the available data from the straight line. For example, in this here you have 1, 2, 3, 4, 5, 6. You have 7 points. That means you have 7 pair data of the time and the drug concentration. In order to know the drug concentration at other time out of this point, for example, here you know the concentration of drug at 60 minutes or at 90 minutes or 120 minutes. In case you want to know the drug when after 100 minutes or 50 minutes. How you do that? For this case, you will predict the drug concentration or drug amount using this equation. And when you adapt to the zero order in pharmacokinetics, you will adapt y, b, and m, and x to appropriate parameter in here. For this example, y bar is the amount of drug in the plasma. X bar is the time. So to predict the decreasing or the amount of drug at any time, y represent here is the AT, or this means the amount of drug A at certain time t. B is intercept when the light cut the y bar here. So it's equal to the maximum amount of drug in the plasma. So we use a symbol represented A0. It's the similar to B. A0 is the maximum amount of drug in the plasma. K, because K has negative value of slope, so plus M will equal to minus K here. And X here to represent X bars here, that means the time. So X here will be replaced by T. So from the straight line here with 7 time point, you can have an equation AT equal to A0 minus KT. A0 is a fixed number. K, you can calculate from any 2 pair points here. So A0 is known, K is known. So you know the values of A0 and K. To calculate the amount of drug in the plasma at certain time t, you just need to put t, the value of t. For example, if t is 70 minutes, you put t 70 here. And then you can calculate the amount of drug predicted after, elimination, like after 70 minutes. So that's the meaning of using the plasma versus time curve to calculate the parameter in zero order kinetics or zero order elimination kinetics. That is for the drug to follow the zero order. For the drugs which do not follow the zero order kinetics, what happened? For the drug didn't follow the zero order kinetics, when you plot the data in the rectangular coordinates, you cannot obtain a straight line like this, and then you cannot calculate. So in this case, you take the logarithm of the y bar and you keep the coordinate for x bar. This the line that you get will turn into the straight line like this. And that's the drug follow the first order elimination kinetics, or just briefly, the drug follow the first order kinetics. And to calculate, so for the purpose of having the graph here, you have the graph here to calculate the elimination rate constant, because from there you will know like how much of drug will be decreased over time. And you want to predict the amount of drug or the concentration of drug at certain time t. So for the drug that follow first order kinetics from the semi-log graph like this, the slope is calculated using this equation, y equal to b times e exponential of m and x, and we know that m is a slope, b is intercept. So, and the slope is calculated by natural log of y2 minus natural log of y1 divided by x2 minus x1. We adapt this equation into the kinetics. The rate constant k to represent, how much percentage of drug decrease over time is a negative value of slope. And you just calculate m and take the negative value of slope, then you have k. And remember, rate constant k is first order kinetics always has a positive value. So if you know any 2 points pair here, the time and the concentration of any 2 points, then you can calculate the rate constant K using this equation. To predict the amount of drug or the concentration of the drug at certain time point, you will use this equation. AT is the amount of drug, or if you use the plasma concentration of drug, you will replace by CBT. Amount of drug at certain time point will be equal to A0 is the maximum amount of drug in the plasma. Time to exponential minus of KT. K you calculate from this equation, and T is the time point you want to calculate. So in general, the drug follow the zero order. We'll have the data on the for the drug follow the order zero kinetics. The data on the rectangular coordinate will be a straight line. For the drug follow the first order kinetic, the straight line just appear on the semi-log graph paper. So that's different when you see the graph. So when you look at the graph, you will know whether the drug follow first order kinetics or zero kinetics by determining the kinds of paper coordinate and look at the line on here. This graph here just to give you more detail about the example in the previous slide. For the 7 time points with 7 pairs of time and drug amount in the plasma, you can construct a straight line like this in the rectangular coordinates. Because this drug follow the zero order kinetics, you can have the straight line in this paper. And from this data, you calculate the constant rate. Rate constant is equal to 0.7832 milligram per minute. That means every minute 0.7832 milligram of drug will be reduced. And then you can calculate initial amount of drug in the plasma, even though from the data you cannot know. It doesn't show apparent A0 or initial amount, but from this data you can calculate and you will have the initial amount. And when you have the value of K and A0 here, you can construct an equation to describe the change or to predict the amount of drug at certain time. AT, the units in milligram, equal to 104.23, this means A0, minus 0.7832 T. So if you want to know the amount of drug at any time T, you just plug the number T here. Then you can calculate the amount at that time. For example, if you want to know how much of the drug can be in the plasma at the time point like 110 minutes, you just put T equal to 110, then do algebra calculation, then you can calculate the amount of drug in the blood at the time point 110 minutes. Even though it's not when you collect the blood at time point 110, but you still can predict using this straight line. For the drug following the first order kinetics from the straight line on the semi-log graph paper, you still can calculate the K value. For example, with this example, the K is calculated to be 0.032 per minute. So that means about 3.2% of drug will be decreased after every minute. And from this data, you can calculate the maximum amount or initial amount of drug in the blood or in the plasma at that time is 80.242 milligram. And to predict the amount of drug in the plasma at certain time point, you use this formula. AT equal to A0 exponential of minus KT. So in this case, A0, you have the number from here, 80.242. And K is 0.032. And T, if you want any time point, you just plug with the number T. For example, if you want 110 you want to know the amount of drug in the plasma at the time point 110 minutes, you should put t equal to 110 and then do algebra. Then you can calculate the amount of drug at the time point 110 minutes. This is a summary about zero-order elimination kinetic. For any drug follow the zero-order elimination kinetic, the rate is constant. It's always have the same rate. It's independent on the drug concentration. Whatever drug concentration, the rate is still the same. The equation for the amount of drug is AT. This means the amount of drug at any time t equal to A0, initial amount of drug in the plasma, minus K0t. K0 is the elimination rate constant, and t is time t. If you have the drug concentration in plasma instead, you will adapt to CBT. That means the concentration of drug in the plasma at certain time t can be predicted by equal to initial concentration minus K0, that's means elimination rate constant, and at certain time t. K0 is the zero-order rate constant. It is calculated using this equation. K0 equal to minus Y2 minus Y1 divided by X2 minus X1. The unit for K0 in zero-order elimination kinetic is mass over time or concentration over time. For example, milligram per hour, milligram per minute, or milligram per hour milliliter, or milligram per minute milliliter. And the K0 is independent of the drug concentration. The half-life is calculated is equal to 0.5 A0 divided by K0. And again, the half-life always the time unit, of course, hour or minute. The half-life represents the time that a half a drug will be eliminated, or half a drug can be remaining in the plasma. And for zero-order kinetic, half-life is not constant because K0 is constant, but A0 is not constant. If you give the drug with different amount, then you can have different half-life. So if you increase the amount of drug used, the half-life will be increasing. That means more drug is given. If the drug follow the zero-order kinetic, more drug or more dose is using, the half-life will be longer. The half-life is not constant in zero-order elimination kinetic. The amount of drug eliminated is constant, but the half-life is not constant. And it's linear in rectangular coordinate or rectangular paper. Example of drug products that follow zero-order elimination kinetics at controlled release drug or intravenous infusion of drug administration. Now we go to detail about example. How to calculate parameter, pharmacokinetics parameter for a drug following the zero-order kinetics. For example, you have a data set like this. So this is drug A is collected or quantified from the plasma. At 10 minutes, the blood was withdrawn, and then the drug A is quantified in the plasma is 96 milligram. Or 20 minutes, the drug is quantified in the plasma is 89 milligram. 40 minutes, 73 milligram, and so on. This is the set data, typical data that you have in pharmacokinetics when you collect the blood and quantify the drug amount or drug concentration. So how to calculate what a step first? Whenever you see the data like this, you must plot a graph. In this example here, this is for zero order, so you will know that's zero order. But in practice, when you have the data, you don't know that the drug follows zero or first order, so you need to plot a graph to determine the order is a zero order or first order. And also from the graph that helps you to calculate further order PK parameters. So determine the order process, zero or first order. Then you calculate the elimination rate constant K. And for zero order, usually we call K0. You calculate the initial amount or concentration of drug in the plasma. You see from the data here, 10 minutes. You withdraw the blood at 10 minutes and have the amount 96 milligram. The initial amount should be 0 minutes, and you don't have it here in the data. However, from this data, you can build the equation and you can predict how many milligram of drug A in the blood. at the time equal to 0 minute. That's initial mole concentration. Then you calculate the half-life. Half-life, that means the time that's a half of drug is remaining in the plasma. Then you build the equation. The equation will help you to predict any amount of drug A at any time t. And in the pK calculation, it's important that you write the units after the number you calculate, and also the units after the final answer in your calculation when you work on the paper. You must write that or report. You must have the unit always on this. Of course, in the exam sub, I always ask you numerical only because that's just too convenient for exam sub. But when you write the report or you calculate on paper, you must write the unit after that. And for any number, when you calculate, make sure that you put the unit after number, because sometimes you have to convert milligram to microgram in the same formula. Now we go to more detail. From the detail here, I plot on the paper and I have a straight line like this. Just normal paper. I can have the straight line like this, plot a graph. And this is the rectangular coordinate and I have a straight line. So I can assume that this drug follow the zero order kinetics because this straight line is linear in the rectangular coordinate paper. The next step, I will calculate the elimination rate constant. Because it follows zero order kinetics, I follow the equation K0 equal to minus Y2 minus Y1 divided by X2 minus X1. For example, I call here X1, I have Y1, X2, Y2, X3, Y3, and so on. So because I have a lot of data here, if I do the manual calculation using the calculator, I can select any pair of time point to calculate for X2, X1, Y2, and Y1. Usually, if I don't have perfect straight line, I will select the point that closest to the line. So to make it more like closer to the average. In this example, for example, I pick up the two first time point here. I have X1 is 10 minutes, Y1 96 milligram, X2 20 minutes, Y2 89 milligram. So plug in number, I have K0 equal to minus Y2 here, I have Y2 here 89, Y1 96, X2 20, X1 10. Put the number in, plug the number in, calculate. I have K0 equal to 0.7 milligram per minute. That means every minute 0.7 milligram of drug is decreasing. The next step, I will calculate initial amount or amount of drug in the plasma. So I select a type point from here. When I select type point 1 and 2 from here, I will select any type point here to calculate the A0, and using this equation AT equal to A0 minus K0T. For example, I pick up this one because I feel closest to the 0 here and closest to the line, so I pick up this one. So this is AT. I consider at the time T equal to 10 minutes. I have drug A is 96 milligram. From this information, I will calculate what is the amount of drug A at the time equal to 0 minute. So plug in the equation here, AT, I have 96 milligram, equal to A0 minus K0T. I have K0, which is calculated here, 0.7 milligram per minute, time T. Because this AT is a 10, so I put the T here is a 10 minutes because this is the time I selected the number. 96 milligram associated with 10 minutes. So I adapt to this equation. I put the number in. I have this equation. Algebra calculation, then I have A0 equal to, I move on here, 96 milligram plus 0.7 times 10 equal to 7. So 96 milligram plus 7 milligram equal to 103 milligram. So I calculate the initial amount of drug in the plasma from this data, A0 equal to 103 milligram. The next step, I calculate the half-life. Half-life equal to 0.5 times A0 divided by K0. 0.5 times A0 I just calculated here, 103 milligram, divided by 0.7. So half-life equals to 73.6 minutes. So that means after 73.6 minutes, a half of drug will be eliminated, or half of drug will be remaining in the plasma. Then I establish the equation in case I want to predict the amount of drug at any time t. I just follow here 103 divided by 0.7 t. So for any t, I can calculate the associated amount of drug at that time. So that's on how to calculate the pharmacokinetics parameter using the graph, the data of time and drug amount in the plasma. And you just use a simple calculator, then you can calculate this data. And again, before you do anything, you need to plot a graph, determine the process, then you calculate the other parameter following this step. So using the calculator, there's a lot of work because sometimes you select the time point. If I select two pair, I have slightly different value to compare with selecting other two time point here. So sometimes the manual calculation is not very accurate. So usually there's software, or you can use Excel to calculate all the data here. Again, I will show you this data, but this time I don't use the calculator to manually calculate it. I use Excel to make it simpler. So first, I still plot a graph. If using Excel, it should take me less than 30 seconds to generate this time curve. It's that easy. You just put a number, and then from the Excel, you can insert the chart, and then you can have it. I will have a separate video instruct you how to calculate the PK parameters with zero order and first order using Excel in another video. So in this case, you Excel I can have this straight line like this. Then again, I look at this here, this rectangular coordinate paper, and it's straight line, so for sure that's zero order kinetic. Because it's zero order, I can use from the Excel easily. I just right click for 5 seconds, I have the equation. The equation to represent the straight line based on this data using the Excel. For the equation from this here, like y equal to minus 0.7832x plus 0.4.23. So from this data, it's equal to y equal to minus kt plus a0. So in this case, 0.7832, that is the elimination rate constant. 104.23, that's initial amount concentration. I can find directly from this equation. I just calculate the half-life manually for this one. 0.5, I have the A0 divided by K0, then I have half-life equal to 66.5 minutes. And then equation, I already have the equation here. I just adapt to the parameter AT equal to 104.23 minus 0.7832 t. So I'm done using the Excel to calculate PK parameter from the zero order kinetics. It's very simple and easy. Now we go to the next order. That's a first order elimination. Most of the drug follow the first order elimination. Just some drug follow the zero order elimination. So first order elimination is very important, and you must know clearly how to calculate some basic PK parameters in here. This is the data set of the drug amount in the plasma versus time. At 4 minutes, the drug quantified is 70 milligram, 10 minutes, 58 milligrams of drug in the plasma, and so on. So from this one, we can calculate the parameter using the manual calculation or using the Excel. And before we go to the calculation, let's review some basics or some summary about first order elimination kinetic. Again, the rate is not constant. For the first order kinetic, the rate is not constant. It's proportional to the amount of concentration of the drug. The equation for amount of drug at any time t is AT equal to A0 times exponential minus KT. Or if you want to use another equation, you can do natural log of AT equal natural log of A0 minus KT. But to me, I always use this equation because it can give me straight the value of A. So I usually follow this equation. And for yourself, you need to determine which equation you use so it will be consistent and convenient for you for the whole course. And in case I want to represent the concentration of drug at a certain time, CBT equal to CB0 exponential minus KT. And to calculate the rate constant, remember this is a rate constant K, is equal to minus natural log of y2 minus natural log of y1 divided by x2 minus x1. And again, the K value always positive for both first order and zero order kinetic. The units for K in first order kinetic is the inversion of time, usually inversion of hour, inversion of minute, that means per hour or per minute. And this represents the fraction of drug eliminated per unit time, not amount, it is the fraction of drug eliminated per unit time. And for this first order elimination, concentration is dependent. It depends on the concentration. The rate depends. It's not constant, and the rate depends on the concentration. The half-life is constant. It's calculated by half-life equal to 0.693 divided by K. This is example of calculation for the drug follow the first order kinetics. Whenever you have a set of data, usually you need to have a set of data of time versus the amount of drug or concentration of drug in the plasma. First, you need to have plot to do. First thing you need to do is plot a graph. You need to plot a graph to determine the order, determine the order process. Then you calculate elimination rate constant, calculate initial amount of drug or the concentration of drug in the plasma, calculation half-life, and establish the equation for the prediction of the drug amount or drug concentration at certain time t. And again, always write the units after the final answer in your calculation if you work on the paper. And make sure that you pay attention to the unit with the equation to make sure that you have the appropriate unit. So for the first order kinetics, something about using calculator you must know. That's a natural log. I give you example. You must know how to use the scientific calculator to take the log or natural log. For example, natural log of 1 equal to 0. Natural log of 2 equal to 0.693. And also you must know how to use a calculator to calculate some exponential value, like exponential of 0.23 equal to 1.259. But exponential of negative 0.23 equal to 0.795. That's the thing you must practice and make sure that you have correct, accurate number whenever you calculate. Now we go back to the data. You have a data set like this. First, plot a graph. And in this slide, I show you the manual calculation, I mean just using the calculator. If you plot, first you start with the rectangular coordinate graph. Remember, whenever you determine or calculate any PK data, you start with the simple thing first. You start with the rectangular coordinate paper and you plot the data. And from the data here you see this is a curve, it's not a straight line. So this one doesn't follow the zero order kinetics. If you take the log of the y bar and then you replot the graph, and you see that's a straight line. So this drug follow the first order kinetics. Because when you determine the zero of first order kinetics, then you can use a product equation. The next step, you will calculate the elimination rate constant. Because I use a manual calculator, to calculate this one, I just need 2 time points. I can select any time points in this data here, or look at the data from the graph. I will pick up the 2 data that's closest to the straight line. In the example, for example, I pick up x1 like 4, y1 like 70, x2 like 10 minutes, and y1 like 58 milligram. I pick up 2 time points here, for example. Then I calculate the elimination rate constant k equal to minus natural log of y2 minus natural log y1 divided by x2 minus x1. So equal to natural log of minus natural log of y2 here, 58. y1 minus natural log of y1 is 70. And my x2 here, 10. Minus 2 x1 is 4. So plug the number in, then I calculate k equal to 0.0314 inversion of minute or per minute. So in this one, the k value 0.0314 per minute, that's the fraction of drug eliminated over minute. Now, the next step, I calculate initial amount or concentration of drug in K. I have drug plasma concentration. From the 2 time points I just pick up, I select only one to calculate the initial amount of drug using the equation AT equal to A0 exponential minus KT. For example, I pick up this time point. I will plug in AT, 70 milligram, A0, the thing I'm looking for, exponential minus k, I have the value on here already, 0.0314. And the t, because I pick up from here, at here associated with t equal 4, so I put a 4 minutes here. Then I will calculate, step by step, 70 milligram equal to A0, and I want to calculate the whole group here first. It's equal to exponential minus 1.256. Then I take exponential minus 1.256 equal to 0.8819. So finally, I calculate A0 equal to 79.37 milligram. So from the data set here, from the lot here, I can calculate the initial amount of drug in the plasma, or maximum in here in plasma, is 79.37 milligram. Then I calculate the half-life using half-life equal to 0.693 divided by K. 0.693 divided by K is 0.0314. Then half-life is equal to 22 minutes. So that means from this data plot here, after every 22 minutes, a half of drug will be eliminated or will be remain in the body. And the equation to predict the amount of drug in the plasma at any time t equal to 79.37 exponential minus 0.0314 t. So if I know the time t, I can predict any amount of time t by using this equation. So you know that the manual calculation using calculator is not like very accurate because it depends on the time point you use. So to make it more convenient and more accurate, we have the Excel, or you can use the Windows software. The Excel is very easy. I still plot a graph, and just within minute I can have a graph, and I still see the curve. So I take the logarithm of the whiteboard, and I have a straight line like this. And from the straight line, I just add the trend line from the graph of Excel. Then I have the equation to describe the straight line easily within 30 seconds. And to use the Excel again, I will have a separate video on showing you how to use Excel to calculate the PK parameter. So, so in rectangular is the curve, and in the semi-log graph is the straight line, of course, is the first order kinetics. Elimination rate constant from the equation I got from Excel, I can see elimination rate constant K equals 0.032 inversion of minute. And initial amount concentration immediately from the equation is 80.242 milligram. the half-life equal to 0.693 divided by K equal to 21.6 minutes. So to compare with the previous one is about 22 point something minutes. This one a little bit like slightly different. But remember the Excel, using the Excel calculation always more accurate than you use the manual calculation. Then I adapt the equation from here to the equation to predict the amount of drug in the plasma at any time t. So Bt is equal to 80 times 80.242 times 2 exponential minus 0.032 t. So if I want to calculate or predict the amount of drug in the plasma at certain time t, when the t is not in the table here, I just plug the t number here, then I have the amount of B. Volume of distribution is a parent volume or a hypothetical volume in which the drug is assumed to be uniformly distributed in. This volume distribution important because it's considered in estimating the drug dosage regimen, and it correlates to the concentration of drug in the body to the administered dose. How to calculate the volume of distribution? I just give you some example. For example, you have a beaker, like here in this graph, and you have a liquid and a drug dissolved in the glass. How to calculate the concentration of the drug in the beakers? You just assume the beaker is just like the body, because in volume distribution, the drug is assumed to be distributed throughout the body. And then the concentration of drug in the plasma will represent or reflect the concentration of drug in the tissue. So I suppose like the beaker here, you just imagine it's just like a body. And the drug it is zoning in here is like the drug in the plasma. How you calculate the volume of distribution? Based on the definition we just mentioned, volume of distribution is a hypothetical volume in which a concentration of drug is distributed within here. So suppose this is a body, and the drug is given to the body at a dose of 10 milligram. 10 milligram is given to the body, and the drug is distributed throughout the body, and you have the blood concentration. Withdraw the blood and you quantify the concentration of drug in the blood here. Initial concentration is 20 milligram per liter. This means the maximum, the concentration you apply after a dose is given immediately here. So how to calculate the dose? You just calculate, it's just like in chemistry, the concentration is equal to the mass of the solute divided by the volume of the mixture. So the volume, you need to know the volume. In here, you don't have the volume. So the equation is similar to the concentration equal to the concentration equal to the dose here divided by the volume of this here. And when we rewrite it, the volume of distribution will be equal to the dose divided by the drug concentration you have in here, or in here is a CB0. So to calculate this, it with a dose of 10 milligram and concentration of 20 milligram per liter, the volume of distribution is 10 milligram divided by 20 milligram per liter. The volume is 0.5 liter or 500 milliliter. So for those 10 milligram, if a concentration of plasma drug quantified 20 milligram per liter, then volume distribution is assumed or calculated to be 500 milliliter or 0.5 liter. That's the way we calculate volume of distribution. In case in the body you give another drug, the dose still 10 milligram, but the concentration you quantify in the blood is 2 milligram per liter. Using this equation, dose divided by the concentration here, the dose 10 milligram divided by 2 milligram per liter, the volume you get is 5 liter or 5,000 milliliter. So the volume distribution is apparent, is hypothetical. It's not a real volume. It's not real physiologic volume based on anatomy of the body. It depends on the property of the drug. In general, the equation to calculate volume distribution is total drug in the body at time t divided by drug plasma concentration at time t. And usually, to make it simple, usually volume distribution is calculated based on the dose divided by initial concentration. And just the picture of I show here in case of one compartment, two compartments. If you look at here, if one compartment model, the drug distributed very fast. After the drug is given, it's distributed in the body, and the concentration of drug in the plasma reflect the distribution here. In this case, you can see the concentration of drug in the blood. Immediately when you measure, it's a high concentration. Because as CB has a high concentration, volume distribution usually high here, you have the volume distribution is small. So that means for a drug is highly, it quickly distributed in the body. For this case, like one compartment model is as in the picture, the volume distribution is low. This is a figure about two compartment model. For some drug has some two-phase distribution or different affinity. For example, the one case, the drug has the high affinity to certain tissue, for example, digoxin. The drug, when it's given to the body, is will distributed more in the organ. In tactile, then it's gradually distributed throughout the body. So in this case, when you take the blood, withdraw the blood, you quantify the drug concentration in the blood, you don't see a lot, just small amount. And it's because small amount of drug, immediately when you give the drug, and you calculate volume and distribution based on the dose, because CB0 here, initial concentration at time is low. Because the CB is low, then volume distribution is very, very large. Similar for the drug, have high distribution to the tissue. Because drug has a high distribution in the tissue, drug concentration in the plasma is small. And whenever drug concentration in the plasma is small, volume distribution is always high, because this one decrease the same dose, then volume distribution will be large. For some drug, here, in case if the drug like distributed in the body, but then most of the drug has a high binding to protein in the blood. Because the drug has a high binding protein in the blood, it stays long there, and when you quantify the drug, you can see high concentration of drug in the blood. And whenever you have a high concentration of drug in the blood, then volume distribution will be, if you have small, high concentration, that means CB here is large. That means volume distribution will be small. So in general, the volume distribution is not a biological value based on anatomy of the body. It is constant for given drug. Some drug has small volume distribution value, some drug has a large. Some drug has less than 1 liter. Some drug can have 7 to 10 liter, or some drug even have hundreds of liter. It depends on the property of the drug. The unit volume distribution usually liter or liter per kilogram. And again, the higher the drug distribution in the tissue, the higher the volume distribution. The higher affinity to the tissue, you have the higher volume distribution. These two cases, you have higher volume distribution because the drug concentration in the plasma is small. However, when the drug has a high plasma protein binding, the concentration of drug in the plasma is high. In this case, the volume distribution will be small. This is an example how to calculate volume distribution based on the initial concentration and the dose. A patient is injected a drug with 50 mg of dose. Blood samples are withdrawn at predetermined time points. Initial concentration is calculated as 1000 microgram per milliliter. What is the volume of distribution of the drug? So we use the equation volume distribution equal to dose divided by initial concentration. The volume distribution will be equal to 50 milligram divided by 1000 microgram per milliliter. Because the units here is different here, we need to invert to make sure they have the same unit. So 50 milligram here we keep here, and 1000 microgram equal to 1 milligram per milliliter here. So volume distribution is calculated at 50 milliliter. You need to be careful with the unit when you calculate pharmacokinetics, and this is a good example. Volume distribution here you have 50 milligram of dose. However, the unit for the concentration is microgram per milliliter. In this case, you need to make sure that you convert the unit in the same unit before you continue with algebra. If not, you have a huge mistake. And in pharmacokinetics, when you do the calculation, always I suggest you to write the unit after the number when you calculate. So in this case, you can figure out, recognize immediately in case whether you need to change the unit or convert the unit or not. And again, pay attention to the unit in pharmacokinetic calculation. The last pK parameter we learned in this lecture is the AUC, or area under the curve. Look at this graph. I think you're very familiar with this plasma drug concentration versus time curve. For the curve, if you calculate the area under this curve, we call AUC, or area under the curve. AUC is very important because it's helpful to calculate the drug's bioavailability. The drug's bioavailability is how much of drug can appear in the blood concentration. So how to calculate the AUC? There are two methods. One of the method is a practical experimental method using the graph and using the trapezoid rule. Trapezoid rule, what is it? How can we use it? For this method, in the curve here, you will divide the curve in different fraction, small fraction, and each fraction you consider this a straight line. Assume that's a straight line because it's small. You can assume that's a straight line. When you link 2 points together, you always have a straight line. And for each fraction here, you assume that's a trapezoid, and then you use the rule of trapezoid calculation to calculate the area. So, for example, in this one, for 2 time point, T2 and T3. T2, you have CP2. T3, you have CP3. And because you assume that's a trapezoid shape, so you can use the rule to calculate the area, and equal to the large side plus small side divided by 2 and times to the height here. So large side here is a CP2, small side here is CP3. So it's equal to CP2 plus CP3 divided by 2. And time here, the T between here is equal to T3 divided by T2. And you have here. And similarly, you can apply for other fraction of the time curve. And then, for example, here, 1, 2, 3, 4, 5, 6, 7. You have 7 time point. You have T1 to T7. So from this equation, you can calculate the pair for each fraction from T1 to T7. However, how to calculate between T0 to T1? Because the area under the curve is assumed to be the area when the curve reaches the Y bar and when the curve reaches the X bar. So to make sure that this is a total amount or concentration of drug in the blood after a dose. So how calculate from T0 to here, and how calculate from here to here? To calculate T0 from here, you also use the trapezoid rule and consider small from T1 here. And T0, how you calculate the concentration here? That's initial concentration. And then you have to calculate the initial concentration, then you use the trapezoid rule. another tricky part is how to calculate the concentration here from T7 to the end. How you calculate this? For this case, we consider here the whole AUC, we consider including total AUC or AUC of different fraction from 0 time to 0 to time infinity. Is equal to AUC from 0, T0 to the T, or in this example, it's T7 you have here. And from T7 or T here to infinity, we consider AUC T to infinity. AUC of T to infinity is calculated based on the formulation is equal to the last concentration in here divided by elimination rate constant. So when you have on the fraction of AUC using the trapezoid rule, then you add the AUC from T to infinity, then you have total AUC. The second method is using the equation. In case you don't have the graph, you don't have the data about this one, but you have the data about those elimination rate constant and volume distribution, you can calculate AUC is equal to dou divided by K times VD. You see dose divided by volume distribution is equal to initial concentration. So AUC is also calculated as initial concentration divided by elimination rate constant. Now we go to example how to calculate the AUC. This is the general steps you need to obtain the information before you can calculate the AUC using the graph. First, you need to plot a graph first. Then you determine the order process kinetic. From there, you calculate the elimination rate constant K and initial concentration CB0. After you have this, then you use the trapezoid rule to calculate the AUC from T1 to T last based on the data you have. Then to calculate the AUC from T last to T infinity, then you use the equation which I mentioned above. Then you calculate the AUCs from T0 to T1. This one, thanks to the initial concentration, you can use a trapezoid rule to calculate this. And the total AUC is include the sum of all AUC you just calculated. And in the calculation of AUC as order pK parameter, pay attention to the units. Always write the unit after the number so you can recognize whether you need to change the unit or convert the unit or not. And always, if you write or you do the final calculation on the paper, always write down the unit. In summary, now example. In the lecture, make sure that you have the data and then you plot the lecture, make sure that you are able in the example you have on the question in the learning objective. You have 5 time and points. This is time one. You have something you must remember, memorize. This there's time is our important order kinetics is a 0 order and first order plasma order elimination is the 30.3 on rectangular microgram per milliliter. Elimination rate at the time point T2 equal to 2 half-life is the plasma drug concentration is 18.4. So for the 0 order, the equation to calculate step by step equal to A0 first you plot the graph T. And you see elimination rate rectangular coordinate equal to minus and or negative convert into semilogarithmic. You have a straight line. So this one is the first order kinetics. Half-life equal to 0.5 divided by the elimination rate constant. The half-life is not constant for a drug. The initial concentration on how much of drug. So from the initial you can calculate or initial concentration of drug. Elimination rate constant. First order so the initial concentration is the most this common. One I use Excel easily. I can have equation. It's linear and the elimination rate constant is 0.5. The elimination rate and half-life and then the initial concentration is 49.9. The elimination rate constant is calculated using the negative slope or is negative of natural log of y2. So then I do step by step of calculate divided by x2. For example, so first I do the fraction t1 to t2. The amount of drug for this one I use equal to trapezoid rule initial amount AUC T1 to T2 equal to CP. And in case you don't use amount of drug, you use CP. You can divided by 2 this equation to the T2 divided by half-life is calculated as plug the number in. I have the first AUC and this is very important T2 equals to memorize 30. Actually on the equation plus 18. This lecture here in this divided by you have to memorize. Subtract divided by 2. Volume distribution is a hypothetical volume in which the drug is assumed to be uniformly distributed. So finally, I have an equation to calculate volume distribution is equal to dose divided by initial concentration. 3.35 microgram area per under the curve hour is calculated. And using either the same method, I will calculate and it's very using the trapezoid rule to calculate the biofraction from availability of a drug. T3 to for T4 and T4 to T5. For the graph, you use a trapezoid rule to calculate the and for the equation you can use AUC equal to dose divided by kVg. I use the equation initial AUC last equal to CP last divided by elimination rate constant. Today lecture. CP last thank you for your attention. 4.1. CP last is 4.1 microgram per milliliter, and K you have 0.5 per hour. So finally, I have AUC last is 8.2 microgram per milliliter time hour. Now I continue to calculate the AUC fraction remaining. This means from T0 here to T1. And I still use a trapezoid rule. AUC T0 to T1 equals CP0 plus CP1 divided by 2 times T1 minus time 0. So CB0 from the graph I calculate, I have CB0 is 49.941 microgram per milliliter plus CP1 we have from the data here 30.3 microgram per milliliter divided by 2 times T1 is 1 hour minus T0 is 0. So finally I have AUC T0 to T1 is 40.1205 microgram per milliliter hour. So then when I have all information I need, then I calculate the total AUC. Total AUC equal to the sum of AUC from T1 to T5 plus AUC from T0 to T1 and AUC of T5 to infinity. I add them together. Finally, I have total AUC is 101 times 79 microgram per milliliter hour. This is a final calculation of AUC. The plot is linear on rectangular coordinates. The elimination rate is constant, but the half-life is not constant. The amount of drug at certain time t, AT, is equal to A0 minus K0t. The elimination rate constant K0 is equal to negative of Y2 minus Y1 divided by X2 minus X1. The half-life is equal to 0.5 times A0 divided by K0. In the first order elimination, the plot is linear on semi-log coordinates. The elimination rate and half-life are both constant. The amount of drug at certain time t, AT, is equal to A0 times 2 exponential minus KT. And to calculate the concentration, you can use the same equation, CPT equal to C0 exponential minus KT. The elimination rate constant K is equal to negative of natural log of Y2 minus natural log of Y1 divided by X2 minus X1. Half-life is equal to 0.693 divided by K. The volume of distribution is a hypothetical volume in which the drug is assumed to be uniformly distributed. Volume distribution is equal to the dose divided by initial concentration CB0. AUC or area under the curve or under the plasma concentration versus time curve. This parameter is helpful for calculating the drug's bioavailability. AUC is equal to dose divided by K times Vg or equals to the initial concentration CB0 divided by K. More practice questions with explanations are presented in the lecture of Mathematical Fundamentals in Pharmacokinetics, Part 2. Thank you for your attention.